written by Neil deGrasse Tyson. Black holes are among the most fascinating objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. Imagine a place where the fabric of space and time itself is warped beyond recognition. This is the reality of a black hole. Black holes form when massive stars collapse at the end of their lives. The core implodes, crushing matter into an infinitely small point called a singularity. The singularity's density and gravitational pull are unimaginable. Surrounding the singularity is an invisible boundary known as the event horizon. This is the point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. Not even light can break free. The very laws of physics seem to break down at the singularity, leaving us with more questions than answers. Yet despite their mysterious nature, black holes play a crucial role in the evolution of galaxies and the universe itself. The event horizon is not a physical boundary. You wouldn't feel anything special as you crossed it, except for the ever-increasing gravitational pull. Imagine it as a boundary in space-time where the escape velocity exceeds the speed of light. Remember, nothing travels faster than light. This cosmic speed limit means that once you're inside the event horizon, there's no turning back. You are forever trapped within the black hole's grasp. Think of a swimmer caught in a powerful current. They might struggle to swim against it, but eventually, the current becomes too strong. The event horizon is like that current, but on a cosmic scale. It's the ultimate point of no return, a boundary beyond which our current understanding of physics can only speculate about the strange and wonderful phenomena that occur. Even the vacuum of space, which we perceive as empty, is teeming with activity at the quantum level. It's a chaotic dance of particles and antiparticles constantly popping in and out of existence. We call this phenomenon quantum foam. These particles are called virtual because they exist for incredibly short periods. They borrow energy from the vacuum, appear briefly, and then annihilate each other, returning the borrowed energy. Imagine a bubbling cauldron of energy with particles constantly appearing and disappearing. This is the reality of the quantum world, a realm governed by uncertainty and probability. These quantum fluctuations might seem insignificant on a macroscopic scale. However, near the extreme gravity of a black hole's event horizon, they have profound consequences. To understand Hawking radiation, we need to delve deeper into the nature of these virtual particles. They always appear in pairs, a particle and its corresponding antiparticle. These pairs have opposite charges and other quantum properties. Think of it like matter and antimatter constantly being created and destroyed in a delicate balancing act. The energy borrowed from the vacuum is paid back when the particles annihilate each other. However, near the event horizon, something extraordinary happens. The intense gravity can disrupt this delicate dance. Imagine the particle-antiparticle pair appearing right at the edge of the event horizon. One particle falls into the black hole, while the other escapes into the vastness of space. Section 5. At the edge of the abyss, Hawking radiation emerges. When one particle from a virtual pair falls into a black hole, it can no longer annihilate with its partner. The remaining particle is now free to escape. This escaping particle is what we observe as Hawking radiation. This radiation carries away some of the black hole's energy. Remember, energy and mass are equivalent, as Einstein's famous equation, E equals mc squared, tells us. As the black hole loses energy, it also loses mass. This process is incredibly slow for typical black holes. It would take an extraordinarily long time for a black hole to evaporate entirely through Hawking radiation. But the implication is profound. Black holes are not entirely black. They emit a faint glow of radiation, a testament to the strange and wonderful interplay between gravity and quantum mechanics at the very edge of reality. Section 6. Stephen Hawking's Legacy, Illuminating the Darkness. The concept of Hawking radiation was first proposed by the brilliant physicist Stephen Hawking in 1974. His groundbreaking work combined general relativity, the theory of gravity, with quantum mechanics, the theory governing the microscopic world. Hawking's insight revolutionized our understanding of black holes. They were no longer seen as eternal prisons from which nothing could escape. Instead, they slowly radiate their energy away, shrinking over vast cosmic timescales. Hawking's discovery was a triumph of theoretical physics, demonstrating the power of human ingenuity to probe the deepest mysteries of the universe. His legacy continues to inspire scientists to this day. His work showed us that even in the darkest corners of the cosmos where gravity reigns supreme, the laws of quantum mechanics still hold sway, leading to unexpected and fascinating consequences. Section 7. Experimental validation, recreating the universe's secrets. While Hawking radiation has not been directly observed from black holes, the phenomenon has been demonstrated in laboratory experiments. These experiments involve creating analog black holes using sound waves or light. In one such experiment, researchers used ultra-cold atoms to create a sonic black hole, a region from which sound waves cannot escape. They observed phonons, the quantum particles of sound, behaving just as Hawking radiation should, emerging from the sonic event horizon. These experiments provide compelling evidence to support Hawking's theory. They demonstrate that the fundamental principles underlying Hawking radiation are sound, and that the phenomenon is not merely a mathematical quirk. While directly observing Hawking radiation from an astrophysical black hole remains a challenge, these laboratory experiments bring us closer to understanding the intricate dance of gravity and quantum mechanics at the event horizon. Section 8. The slow fade of black holes, evaporating into nothingness. Hawking radiation has profound implications for the fate of black holes. As they radiate energy, they slowly lose mass and shrink over time. This process of evaporation is incredibly slow, especially for massive black holes. Think of it like a tiny leak in a vast reservoir. It takes an immense amount of time for a black hole to evaporate completely. However, the implication is clear: black holes are not eternal. As a black hole shrinks, its Hawking radiation intensifies. The final stages of its evaporation are thought to be quite dramatic, culminating in a burst of energy. However, this final act is still purely theoretical. The evaporation of black holes represents a profound connection between the largest and smallest scales in the universe, from the immense gravity of black holes to the subtle world of quantum mechanics. Section 9. Conclusion: the universe's grand tapestry. The story of Hawking radiation is a testament to the power of human curiosity and our quest to understand the universe. It's a story of the interconnectedness of seemingly disparate realms of physics, gravity, and quantum mechanics. Hawking radiation reminds us that black holes, once thought to be cosmic dead ends, are dynamic objects that interact with their surroundings in subtle but profound ways. Their slow evaporation through Hawking radiation adds another layer of complexity to the grand tapestry of the cosmos. As we continue to explore the universe and probe its deepest secrets, we can be sure that new discoveries await us. Discoveries that will challenge our assumptions and redefine our understanding of the cosmos, and perhaps, just perhaps, will unravel the remaining mysteries of black holes and their ultimate fate.